This is a short announcement to explain why our presentation seems to be short on some of the parts. As you can see, we hide many slides due to the time constraint, so please check those slides for a complete presentation.
Our product is a leg up by Alexander, Ryan, Eric, G, and Zipeng. Our design is a knee brace that uses spring and damper to reduce forces on the knee. It is designed to help people with a wide variety of knee injuries recover and increase their mobility. The brace can supply up to 10.5 newton meters of assistance at 80 degrees from the highest setting. We found this with a substantial amount in relieving stresses from the knee and leg. The damper can provide up to 10.5 newton meters of resistance for high stress situations such as descending stairs. Our product manufacturing costs very low at 110.83 cents, allowing us to competitively compete in the current market. We are currently at the prototyping and testing phase, where our product will be refined before we plan to bring it to market.
Due to our use of bolts and nuts, along with clever use of space, the only part that requires simple stack-up analysis is the spring housing. As calculations shown above, the tolerance is not an issue for our design. For human factor consideration, we did an REBA scoring with stairs descent. We found there to be For human factors considerations, we did REBA scoring with stair descent. We found there to be fairly high scores. You want to reduce stress applied on the knee and legs. We decided to reanalyzing our knee brace and choose to reduce the risk of pulling on and off the knee brace. After analysis, a release mechanism that allows the user to bend their legs and remove the brace is preferred, which can also allow the user to sit down with the knee brace on. This mechanism had to be reliable without any accidental release.
So these are our force calculations. Part of knowing what damper and spring to use involved understanding the forces that would be at the knee due to the user's weight when the user is bending the knee. So using population statistics available online and previous research, we were able to calculate the torque range that we would expect at the knee joint. The upper range of the torque was calculated using the heavier end of the male population, and it's expected to be about 10.5 newton meters. The lower range calculated using the lighter end of the female population is 7 newton meters. Based on prior research done by other studies, the average knee angle when going down the stairs is about 80 degrees. So we would want to design our damper and spring to compensate for these values when having rotated 80 degrees. So here's a closer look at the damper subsystem. The damper subsystem, basically, what it does is it takes force from the user's leg and transfers it through the arms shown in green and orange, which then transfers it to the rotary damper shown in yellow. Basically, it slows down the user when they rapidly bend their knee to prevent overextension, and it works in conjunction with the spring to act as basically a shock absorber. This is great for activities such as going down the stairs or squatting when the user is moving rapidly in a downwards direction. And we want to slow down the user's body by slowing down the speed at which they're bending their knee. Here's our damper. It's found online, also known as a rotary speed limiter. It's about 90 millimeters long. It's expected to provide the 10.5 newton meters of torque that we calculated earlier. This is the damper housing. The steel damper needs something to shield it from the environment, so the housing was designed to hold it. Has holes for bolt screws, rivets. This is the housing cap, again, to shield the damper from the environment. Here are the rivets used to attach the damper to the damper housing. This is publicly available from McMaster. Here are the flathead screws used to attach the housing cap to the housing. Here's the spring subsystem. Spring subsystem works the same as the damper subsystem. Again, the force on the user's leg is transferred through the arms, shown in orange and green, into the torsion spring, shown in purple. The spring absorbs heavy impacts at the knee joint, and then later uses that energy to help the user strain their leg again, which again is helpful for activities such as descending the stairs, squatting. Spring housing also uses a pin adjustment system, which is the pin shown in blue. This allows the user to manually compress and decompress the spring based on their needs. So if the user feels that they're rehabilitating and their muscles feel stronger, they can choose to manually decompress the spring, making it weaker. And when they bend their knee, more of the forces will go through their muscles, and less of it will go through the spring. This is the torsion spring. We used an online retailer that makes custom springs to spec it based on, they had an app on their website. So we expect it to have the torque that we needed based on calculations that we did earlier. This is the ball bearing. It allows us to fit the green arm shown earlier into the housing. It is a press fit joint, which we will show later. This is the pull pin. The pull pin is another part that is found online, so we won't go into the details of it. It's basically a pin, and then there's a housing with a spring inside that allows the user to pull the pin back. Another housing for the spring, the shield from the elements, and then the cap that goes with it. This is the strap subsystem, which includes the arms and the strap. So this is the damper arm, which has a shaft at the end to allow it to attach to the rotary damper. The spring arm also has a shaft. There's also a slot in the shaft to allow the inside of the spring to be fit into the shaft. And then this is the housing arm, which has holes for bolts to attach to the housing. You notice that the arms also have two sets of clips, which allow it to attach to the strap. This is the bolt that attaches the housing arm to the housing. And this is the lock nut that we're using. The lock nut is a serrated flange lock nut, which we chose because we expect high levels of vibrations in the housing, and the serrated flange lock nut will resist some of those vibrations so that the connection does not loosen over time. And then this is the strap. It's made of nylon. It's approximately 120 millimeters long, but is otherwise flexible to be able to conform to the user's leg. And there are loops in it to allow it to fit into the clips of the arms.
Our team performed design failure modes analyses on 3 important functions of our product: to relieve stress from the user's knee, to be able to safely secure the product to the user, and to adjust the tension in the spring. This analysis helped us discover which failures were most critical to the safety of the user. Our team sought to resolve these issues first, as they have the most drastic effects. The potential failure modes that still have the highest risk priority numbers are the risk that the product does not relieve enough stress and the risk that the straps cause pain to the user. Our team plans to mitigate these risks by increased prototype testing. The prototypes of our team seek to answer several questions on corrosion resistance, comfort, and durability of our product. Our early prototypes include the spring subassembly and the damper subassembly. A simplified version of these two subassemblies will be prototyped and then attached to potential users to assess the effective assistability of the device. After the initial prototypes have been designed and tested, a later complete prototype of the unit will be built. Early prototypes will be made using CNC milled aluminum and 3D printed parts, as they are far less expensive to manufacture than the initial cost of a die for casting. These parts may need to have increased dimensions to compensate for the lower strength of aluminum or 3D printed components. Several tests will be performed on the prototypes. A test apparatus will be made to gain numerical values on the deflection that the prototype produces. Several sample users will be involved in trying the prototype unit in order to evaluate the real-world performance and ensure that the product meets the needs and requirements of the target population. If our test results show that our product needs improvement, our team will incorporate the changes into our design process.
All right, so I will be examining a material selection for our spiral torsion spring. So geometrically, we need to be considering the outer diameter, the inner diameter, the maximum angular deflection that we need, the weight of the spring, and the number of coils we need for the spring. And from there, we can then examine a few more properties in relation to the torque needed for this spring. So we know our max torque is going to be 94 inch-pounds, and we know our angular deflection at a maximum has to be 250 degrees. So then the other 4 properties here can be adjusted as we see fit and as they fit geometrically. So we are pretty limited when it comes to materials for springs, but we will be comparing stainless steel 302 and phosphor bronze. Obviously, I could be comparing stainless steel 303 with 302, but for the sake of argument, we'll compare a little bit to different materials. So we know that the density of stainless steel 302 is quite lower than that of phosphor bronze. And this is really ideal when it comes to wearable technology because you really want to decrease any amount of weight that your user has to carry around with them throughout the day. And we also know that the modulus of elasticity for 302 is a lot higher than that of phosphor bronze. And combined with the good fatigue strength of 302, that will perform really well in a spring that has to undergo thousands of cycles in a day of walking, for example. So from there, we can begin to look at a manufacturing process for this custom spring. So we're really going to be examining a coiling process, as seen in this video on the bottom right. You have your material stored as a steel coil, much like the picture in the top right. It's then run through a channel in a spring coiler machine, and then twisted to form the correct number of turns in your spring. It's then slightly unwound, cut at one end, and then more material can be slid through the channel to make your next spring. What's great about this is it can all be performed at or near room temperature. So our assembly process is actually fairly simple. It doesn't take any kind of specialized tooling. You really only need a rivet gun and a hex driver. And we would recommend just assembling the damper side with the damper and the damper housing and the legs that are attached to that. Then you assemble the spring side with the spring housing and the legs that are attached to that. And then you simply put those two together using the straps that are already part of the design. So we can roughly estimate the cost of manufacturing one of our products using known values for standard parts. Seen here, we used a discount rate of 35% for all of these. And then we also estimate costs for all custom components. Most of those we assume we're using die casting. Obviously the coil spring, as mentioned earlier, is going to be using that coiling process. So through those estimations, we also add an 85% overhead rate that raises our cost to approximately $110 per unit. So along with a manufacturing plan, we also need to come up with a quality plan for numerous components. But in this example, we're just going to be looking at that same spiral torsion spring. It's quite lengthy, but to highlight a few things, we're really just looking at the torque that it can output at the specified angles, that we know it should be outputting this torque at this angle, and that's really what we want to be sure of through this quality plan.
Our final design reduces stresses on the knee by adding resistance to the knee through damper and spring. The spring supplies assistance while the damper limits the speed of the knee, reducing injury risk. The adjustable spring strength provides assistance to a variety of users, allows the user to adjust the assistance as needed. What differentiates us from competitors is the addition of a damper to limit the speed and the side-mounted spring. The damper is an additional safety mechanism, while side-mounted spring reduces rubbing in the back of the knee, a problem our competitors had who mounted springs underneath the knee. The main advantage of the knee brace is the affordability and competitive price that makes it available to a larger audience. Using complete product development process has several positives and negatives from our experience. Forced us to dive deep into our target customer and create a complete list of customer requirements. This made us really consider characteristics we might have originally thought of and analyze what customer requirements were more important than others. It also made us really look into a wide variety of solutions to our problem, making us create a unique solution. Some issues we experienced were COVID restrictions limiting our ability to contact our original audience, the elderly. We found this to make us miss some customer requirements that were needed for our original target audience, causing our product to be better suited for a new audience. Another issue we found was that the process was very lengthy and gave us less time to refine a product in a limited time frame. Our design weaknesses are currently unclear. Our next step is to build a prototype and to test it. We expect there to be several design issues that will arise from this product testing. Some issues we expect to have to address are lack of support on the knee and uneven forces on the knee. We want to wait to address these issues as we are unsure of the area that the knee that these issues might arise and to want to add weight to the brace if it wasn't needed. We expect that our product will need several design iterations to refine our product and have it ready for the market. Our design is competitively priced and can be helpful to many users and after some more product refinement. Thank you.